All right, now we're getting into kind of the meatier parts of the calculations. We're going to calculate our predicted scores and some of the sums of squares in this video. And I'm breaking this up just because this can be kind of a wall of numbers. So I want to try to keep it in manageable chunks for you. All right, here is our regression equation. Y prime is equal to 22.3 plus 0.0552, the slope, times whatever the score is on X. We're going to use this to derive a predicted score. And what that means is for every single person, whatever their value is for X, we're going to plug it into this equation and calculate an individual Y prime value. You can see I've done this here. I've got a couple of examples here. You can see the first person, I plug their X score of 16 into the equation, and I get 31.14. The last person, X of 10, I plug them into this equation, and I get 27.82. And you can do all of the other calculations on your own if you want to give it a shot. So what do we do with these predicted scores? Well, you know, you can look at them and you can say, oh, well, wow, person number 3, we were really off in our prediction, or person, the final person, we were really off there. But some of these are really accurate. You know, the person who scored X of 32 and Y of 41, well, we predicted them about 40. We can look at it that way, but it doesn't really get us anywhere. We need to kind of formalize that. And that's what we're going to be doing with a new set of statistics. And this is really the heart of statistical procedures such as regression and analysis of variance, which in my mind are like the two giant titan statistics in this class. Really two of the workhorses within psychology. So the same logic works for both of those types of procedures. We're going to calculate a set of sums of squares statistics. We've actually seen a sums of squares statistic before. The numerator of the standard deviation, sum of X minus X bar squared, that is a sum of square statistics. All sum of squares mean is that we square some stuff and then we take the sum of it. There's going to be 3 different sums of square statistics that we're going to calculate here, and they're going to tell us things about how good our prediction is, how bad our prediction is, and the total amount that could possibly be predicted. So we start with sums of square total. Sums of square total is asking how much is the Y score moving around? How much does it tend to vary? Or another way to think of that is if we were explaining everything, how much would that be? Sums of square residual is going to refer to how far off our prediction is from the actual score. And that's going to be a function of the difference between the individual score, Y, and our prediction. So when we were looking at these things and saying, oh, wow, this score is kind of far off from the predicted score, that's going to contribute more to the sums of square residual than the ones with smaller values. The last value is sums of square regression. How much does our prediction tell us that we didn't already know? Without any information about the relationship between X and Y, I know that the mean for Y is 35. If I know the mean for Y is 35, that's a baseline piece of information I could use. I could use that and I could just guess everybody's getting a 35, and I would have some level of accuracy just by knowing the mean. What this is asking is what does Y prime tell us over and above what the mean already tells us? And one thing that we'll see is if we have absolutely no relationship between our two variables, Y prime will actually be equal to the mean. It'll be the same thing as the mean. So how much does this tell us that we wouldn't already know by knowing the mean? Sums of square residual is often called error variance or unexplained variance, whereas sums of square regression is often called explained variance. Again, used extensively in regression and ANOVA, probably by far the 2 most important pieces in this class, the ones that I get the most excited talking about as well. You can see sums of square total is always going to be the sum of sums of square regression and sums of square residual. So you can think of that as just getting broken into 2 parts. And it does involve some extensive calculations. I don't think that the calculation part is hard. I think that there is, however, a lot to it, and that can be very challenging. All right, sums of squared total. Oops. Sums of squared total is the sum of y minus y bar squared. So that looks just like what the numerator for the standard deviation was, except we're focused on the y scores rather than the x's here. The first step is to take each score and subtract the mean from it. So I've taken each score and subtracted the mean. We also did that with the covariance, so with something we're familiar with. The next step is to take each difference score and square it. So that first score, -10, becomes 100. And then finally, in the last step, we simply add up the results from that y minus y bar column. And this ends up summing to 700. One thing of interest that we'll see, and we'll see this with all the different sums of square statistics, if we summed before we squared, the sum of y minus y bar would always be 0. All of these statistics are always going to produce that. They're going to have half above, half below. It's always going to add to 0. So that's part of the reason why we need to square things, so we get some other index.